Linked list before. The linked list we saw before, anybody recalls the name of the linked list we saw before?
Singly linked list?
So we've seen a singly linked list. Thank you, Brendan. So we've seen a singly linked list before. What do we know about singly linked list?
I think there's only a head.
Well, there's a head.
Or like you can't do previous and next, something like that.
Yep, something like that. Very good. So we have next. Both linked lists have head and there's tail, right? Doubly linked list also has it, but you did bring up a next pointer. So the singly linked list has a next pointer, but it does not have, I think you said previous, right? Chelsea?
Yeah.
But it does not have previous. Very good. So that is what we know of a singular linked list, right? We know there's a head, there's a tail, there's a next value, which is the next node in that particular linked list there. So that would be part of the node class, right? And we have some sort of value, again, also in the node class. Great. So in a single linked list, if we were to draw it out, a singular linked list would look like a series of nodes. Call this 10, call this 7, call this 5, and this is pointing to 0. So here is our singly linked list of nodes. And Chelsea said we have a head, we have a tail, okay? And here we have the next pointer to the next node, right? So as we traverse through that linked list, we traverse from the head, we go from head to the next node, to the next node, until we have nothing else to visit, right? There's no way to say 5, what is before you right now, right? There's no like next, there's no previous node here. So I cannot say 5, what's before you? If I have to do that, I have to go reverse, right? So that's a singular linked list. You could go one direction from the head to the tail, okay? This is what we saw before. Today, we'll take a look at a doubly linked list. Today, we'll take a look at doubly linked list. Okay. We have 10 again, we have 7, and we have 5. So let's see what the differences are. Well, in the doubly linked list, you still have this next pointer. You still have a next pointer. So 10 is pointing to 7, and 7 is pointing to 5. We still have our head. We still have our tail. Okay. But now we have a difference. Now we're able to say, 7, what's your previous node? Right? 5, what is your previous node? Head, what is your previous node? So now we have 2 pointers. We have a next pointer, and we have a previous pointer. Okay? So now if we are tail, we could go to head. From tail, we could go to head. How can we go to head from tail? Well, we could say tail.next, tail.previous, right? That previous, keep going until you get to head, right? So I could go forwards and backwards very easily with my doubly linked list, okay? So the big differences between the doubly linked list and our singly linked list are we have 2 pointers in our doubly linked list. There's 2 pointers, there's a next pointer, and there's a previous pointer, okay? It's faster to get through things, right? But at the same time, the memory footprint is bigger because you have more memory. You're taking up more memory, you have 2 pointers now as opposed to 1 pointer, okay? So doubly linked list here has 2 pointers. A singly linked list has one pointer. Okay. This takes up less memory. And the doubly linked list takes up more memory. The doubly linked list also faster access to nodes. Okay. So those are the two differences between those two data structures here. Any questions before we continue?
Alex,
Yes.
it doesn't end in a, or it doesn't, after 5, it wouldn't be nil?
Yes, it has a nil pointer as well. Thank you.
Okay, cool.
Very good. Yep, yep. And then head here, the previous pointer is pointing to nil. Very good, thank you. Very good. Okay, let us now we'll go back and forth between our playgrounds and our whiteboard as we write different methods in our doubly linked list class. But for now, let's go to open up a new playground. We'll open up a new playground. Let me get a new window happening here. So Xcode, file, new playground. It's a playground, blank playground. Click next. List. We name our playground doubly linked list. We click on create. And here we have our doubly linked list. Let me make this bigger. Okay. So as we have our linked list node, we'll start off with a node class. Implement node. Start off with a class. I'll actually call it doubly linked node. The properties we have some sort of value. We have a next pointer. Here it's optional because maybe it's not pointing to anything. And we also have a previous pointer. Okay. And we'll have an initializer here to initialize our value. Value. And one other thing I want to show us, so type that out, and then I want to show us one other thing here before I type it out. Are we okay? Can I go back to the whiteboard?
Yeah.
Okay.
Yeah.
Cool. So here we back out our whiteboard. And before I code this out, so if we have a node here, call it 17. 17 is pointing to 5. 5 is also pointing to 17. Anybody recall anything that's happening here right now? We have two strong pointers right now. Right? That's what we have in our code here. Right? Next and previous, they're both strong pointers or strong references, right? Anybody want to walk me through what's happening here and how can we make this better? This diagram, I think we use that same sort of diagram when we're talking about memory management. Here we have two strong references.
You're saying to fix it how? Like what are you alluding to?
I'm just trying to see if we could get to fixing it. Like, what's happening here? Is that okay?
I think you're trying to say that we should make some of them, either one of them or both of them, weak variables.
Very good. That's what I'm looking for here. Because if 17 has a strong pointer to 5 and 5 has a strong pointer to 17, what happens here is a retain cycle.
Yeah.
Right?
Would that actually show up as like a purple error, or is it just?
It wouldn't be a purple error. It would just be an optimization error, a performance error, a performance problem, a bottleneck.
Yeah.
Eventually your app will crash with an exit sort of crash there. Eventually you'll get a memory crash. Christian?
Yeah.
So that's what I was looking for. I was looking for, we have a strong retain cycle, right? I'm holding on to you, you holding on to me. We cannot drop each other.
Right. I hope you wouldn't.
One of us needs to have a looser grip onto the other one, right? In order for us to eventually break apart, right? So to achieve that, we'll make this particular pointer weak.
Okay.
Right? So I'll actually just, instead of making it strong here, I'll just kind of put a dotted line. Okay? Very good. Thank you, Matt. So going back to our code here, if you have a variable, if you say var next, this is strong. By default, this is a strong reference. Everybody with me?
Yes.
When we go back to our delegate and we say like var delegate, if I create some sort of delegate like this and I say random delegate, right? This is strong by default. Everybody with me? Yes?
Yeah.
Yes.
Yep.
So that's why we say weak here, in order to have not, I don't want to have my delegate, I don't want to have a strong reference back to my view controller, right? So I say weak here, sorry. I say weak here. Because if I say strong, I'm going to have eventual memory leaks and eventually my app will crash, guaranteed, right? Okay, very good. So by default, same as this is public by default. By default, this is strong. Strong, right? So next, previous, we said this one is going to be weak. Now we can continue on. So here we have our double link node. We have a pointer to a next node or next value, and we have a pointer to a previous node or a previous value. Okay. The difference between a doubly linked list and a singly linked list would be this. If I was to create a singly linked list here, this would not have a previous, and this would be my singly node. And this is implementing doubly node. Any questions so far?
Yeah, I feel like this is the first time I've used, at least in a really long time, I've used a weak variable outside of like we're doing we're using like weak self for the. It's been a while since we've used like a conventional weak variable. Can we go over again how this?
You would use it like if you create a delegate, like of course a custom protocol delegate, you'd use it on that weak var here, right? So weak says I don't have a strong reference to it. So anytime the thing itself gets deallocated, I myself am deallocated because I don't have a strong reference to it. Matt?
Yeah, I'm hearing you. I'm
right.
Yeah.
So 17 has a strong reference to 5.
It's okay.
5 doesn't have a strong reference to 17. So anytime 17 is deallocated, 5 itself is deallocated. Or 5 itself is not pointing, it's not no longer pointing to 17.
Got it.
As opposed to if it was a strong reference, it would still point to 17. 17 is no longer in memory. Well, it's still in memory technically, but 5 now is pointing to an empty point of memory.
Okay, yeah.
So observing that, like here we observe it because we know we have one node and that one node cannot have a strong reference to 2 things. Right? In your code, there's places you're not gonna see it until it crashes your app.
Hypothetically, what would happen if both of the variables were weak?
If both of the variables are weak,
Yes.
well, you need one of them to be strong. Other than that, it will just get out of scope and you will not have access to it.
Okay.
Right? It's very similar to like if you have your view controller set up and you have a view on it and you make a weak view, anytime your view controller gets out of, your view controller is not going to be strongly connected to that view. And you'll have a lot of issues really quickly.
Okay.
Because the view controller relies on that view. And if the view has a weak pointer to it, anytime that view is gone, the view controller is not going to have the view anymore.
Okay. I guess I was wondering if the weak was like a way of circumventing the issue of yeah. Okay, that makes sense.
Sure? You good?
Yeah. Yeah. Yeah.
Okay. Cool. We are good here. Let's actually start implementing. By the way, just to give us some more context, most times you'll see a problem dealing with like linked lists, you'll be given some sort of class like this. It's not going to be a class with a head and with a tail. Everybody with me? It will be a series of linked nodes. So the way this is going to happen, that's all my code. The way this will get implemented, I'll say, if I create like a doubly linked list here, well, I wouldn't do this. I would do some node 1. Node 1 is doubly linked node, and then give this a value of 5. Actually, let's use 10, which we had earlier. So the way I would have to connect those is I would have to connect them manually, right? I would have to say node 1, well, create the next node, node 7. Node 7 would be some node 7. And the way I would connect those up, I would say node 1.next equal to node 7. I have to say node 7.previous equals to node 1. Everybody with me?
Yes.
Right? So I would have to do this manually, right? But most times you're given like some sort of lit code problem or whatever, you're given like a node here, a node class, and behind the scenes, the connections have been done for you, right? In class, we've done this before, but you have to do it all manually, right? This is just a node class with linked nodes. It's not a linked list class. Everybody with me? Hello?
Mm-hmm.
Okay, but if I have a linked list class here, I could say linked list. Actually, I just call it singly linked list. Like that. And this guy would have some sort of head, which is a singly node. It would have tail, single node, and then I would have my functions here, right? So a singly linked list class would have a head and a tail. Everybody with me so far? Hello?
Yeah.
Yes.
And I would have my functions, like I would have a function append. It would just add to the linked list and so forth and so on. We'll do something very similar for the Doubly linked list, but I just want to make us realize that there's differences there. You could see a node class being used as a linked list, right? And you just link the nodes like this manually, okay? If it's a linked list, if it's a lit code problem, the nodes are connected for you already as a test case or whatever, and you just have to implement whatever they're asking you to implement. Okay, cool. So let's continue on. We have implementing Doubly linked list node class. We have that already.
Sorry about that. Can you scroll for like 2 seconds?
Up here?
Yeah, just this.
This one we're not going to implement because we've done that already before. We've implemented a singly linked list. We've implemented a singly linked list before.
But
I just missed. I just missed what happened.
Was somebody saying something?
yeah, but the other one you had put it that it was a singly node or a single link node.
The one I removed earlier?
Yeah, but you had the DL node. Does that matter, or was that just to show?
That was just to show.
Okay.
That was just to show. It was a DL node. Like if I have to create manually linked DL nodes, I have to do them manually, like say
Yeah.
.next and all of that.
Okay.
That was just to show. But we'll be actually writing functions for that. Like I'll have a function called append that'll append a new node to my doubly linked list.
Okay.
And internally, it will do the connecting the next and the previous and so forth.
Gotcha.
Very good. So we just use like append on it as opposed to doing everything manually every time. Very good. Okay, cool. So now let's go ahead and implement doubly linked list. And here, this is a linked node, right? A node. And here, this is actually a linked list. Okay. We'll start off with a class here. We'll call it doubly linked list. And as Chelsea said earlier, we also have a head here. We use the doubly linked node, right? And we have a tail. And the first function we're going to write is a function to append some value, append some value to our doubly linked node or list, doubly linked list. Sorry, we're given a value, we add it to our doubly linked list. This is the first function we'll write. Okay. All right. Everybody wrote out the boilerplate class here.
Yep.
All right. Let's go back to the whiteboard and do that with our whiteboard, and then we'll go and write the code. So we'll have append the function. It takes in some sort of value. All right, great. Well, what's the first scenario here? We're doing a whiteboard exercise. The function is to write a function that takes in a value and appends it to some doubly linked list. All right, so write a function that takes a value and appends it to a doubly linked list. Okay. Right. Write a function. What's the input? A value. No output. Okay. Anybody want to tell me how they would attempt this?
Anybody want to tell you what?
I'm sorry? No, how would you attempt that problem? If I was to stop lesson right now and say, go ahead and write my append function for me.
Write a function that takes a value and appends it to a W.
Alex,
Yes.
would it be that you would create a node from that value and then?
Okay, so Amini says create a node. Makes sense here. Create a node from the value, yeah?
Yeah, and then assign it as the tail.
Okay, so we'll take it one step at a time, right? So one step here, you say create a node. Okay, let's go ahead and do so. How do we create a node? Well, we have, we'll just say let new node here.
Node, parentheses 7 or 8, whatever.
Very good. DL node, yeah? Very good.
Mm-hmm.
And then here we have, what's the first thing we're gonna add? We'll just add 10. You said 7?
I think we already have 7, so we can do 8.
We just, okay, 8 is fine. For now, there's no assumptions being made. We don't know how many nodes we have.
Okay.
Is that fair?
Yeah.
All right, very good. So here, create a node. Amini says, create a node. We have a node. Great. Somebody else.
Sorry. If we're gonna whiteboard like the thing, we'd ask you, right, if we can guard now or later, right? If there is
Well, let's write our function body and then continue on here. So function, we'll call it append, and the value is some integer. And Amini said, do this. Put that down here somewhere. Okay, so you were saying to guard earlier, Christian?
yeah.
All right, so let's go ahead. What are we guarding against?
We're guarding against well, when we're appending, I don't think we actually have to guard, right? I think I was getting ahead of myself.
Matt, you were saying something?
Yeah, no, Christian, I think you were onto something actually. From if I remember correctly, we have to guard for the last node to make sure that it's not an empty linked list, or that there's
Okay, so you're saying guard here?
I
And you said last node, right?
yeah.
Which is tail, yeah?
Yes. So you guard to see if the last node is the tail. Like guard last node.
Is there a last node, right?
Checking if there's a last node, and if there is, you're setting it up against tail to check that, and then if it's not, then the new node, the node that we're creating, should be the head and also the tail.
Okay, so here we're reaching somewhere here. So now we have, this is good. We're working together. So we have a last node here. Right, so far so good?
Yep.
Yeah.
And here we'll return, obviously, just return nothing. Okay, so if in case there's nothing in the list, right? This is scenario one almost. That's what Matt and Christian are working towards here. The list has nothing in there. We guard it against tail. Let me fix this so we could see this properly. Last node, tail. So class, what Christian and Matt is saying is, let's see if tail exists. If tail doesn't exist, we have an empty list, right? If tail doesn't exist, we have an empty list, right? If we have an empty list, actually, we have a little bit of more stuff to do here. I think a mini stuff probably needs to come first. Here, let's take this guy and put it up here. Sorry. Apologies, I'm just trying to make this better. Okay. So we'll create our node at the top here like that. Great. Because now we have access to new node. Okay. Great, perfect. So now we have the new node Amini created earlier. We have a guard statement. Matt and Christian said we need to guard against tail, make sure tail is not nil. If tail is nil, what do we do? Somebody else. If tail is nil, what do we do?
Do we make the new node the tail?
Yep, very good. So if tail is nil, we'll just say tail equal to new node. And head as well. Okay, so what does that look like? Well, if we put in an 8, it's just gonna be 8. And head is pointing to 8. And tail is pointing to 8. Any questions so far?
I understand what we did before when we talked about the head and the tail.
You said you understood up to before head and tail?
No, yeah. Actually, the drawing just clarified it for me, so I got it.
Oh, you got it. Okay. Yeah, drawings are good. That's why I really talk about DSAs and drawing, right? I think the two of them come in hand in hand. There's a reason why it's whiteboarding, or right? They call it whiteboarding, because you draw, you understand. Just coding is not enough. You have to draw the thing and understand it. Very good. Any other questions? This is very important stuff there. This helps us review linked lists, plus going forward into creating a doubly linked list, right? Some of that we've seen before. Most of it we've seen before. So if anything, it's review plus seeing some new pointer assignments. We good? So if I was to stop here, we all could finish the append function, correct?
Negative.
All right. Okay, cool. So we kind of finished case one, right? So let's just call this case one. Case one. Great. Let's keep going. Okay, so if I have, this is what my linked list looks like right now, right? I have tail here. I have head. Okay. And I want to enter a different value. So now I have a new node. Somebody give me a node, any number, it doesn't matter.
15.
12.
Actually, you could use 12 because I was thinking 12 at first before I said 15.
All right, so we have 12. And again, our function is called append. So we just add into the end. Great, so now we have 8 existing. We want to add 12 as the new node. Let's see what that looks like. So here we have 8. We want to add 12 to it. Well, 8 is the head. We're not doing anything with the head. We want to add 12, like that. What do we know about doubly linked list? Well, there's a next pointer. So 8 is pointing to 12. What else do we know?
We have a weak pointer coming back from 12 to 8.
Very good. So 12 has a previous pointer pointing to 8. Very good. And now 12 is just pointing to nil.
And we have nil right at the end of 8.
Yeah.
And
what do you say?
we have nil for 8 as well, right?
Well, 8 next pointer is 12. And 12's next pointer is nil.
The 8 previous pointer is nil, right?
Yes. Yes, 100%. Very good. This is where we headed. Any questions about that? That's what we need to code. That's what we need to code now. Any questions about that? All right, let's see what that looks like. We have a bit of an arithmetic, pointer arithmetic to do here. We have access to the last node. The last node is this guy down here. Do we all agree that 8 is the last node in this scenario?
In the previous direction.
When we got it, we said, is tail existing? Tail exists, right? Over here? Yeah?
Yeah.
Okay, so that means our last node's value is 8, correct?
Yes.
All right, very good. So over here, 8, we haven't done anything yet. We haven't connected anything yet. Right now, we only have access to the last node and our new node, right? We have our new node and we have our last node. This is our new node here. All right, so we have both nodes. We have our last node and we have our new node. Now, the only thing we need to do is connect them up. Anybody want to help me here? I want to connect 8 to 12. What am I writing out?
Is it, what is it? Yeah, but what's the name of that node? It's
So we have last node and we have new node.
So it'll be last node dot next.
Last node dot next, yeah,
Is equal to new node.
is equal to new node. Is equal to new node. So what Tiffany just did here, she said last node, which is 8. Last node, which is 8. Next here, next is new node, right? We all agree?
Yes.
Okay.
Yep.
Somebody else?
Yes.
Okay, very good. Somebody else? We're not done yet, right? Because we
No,
have,
Previous.
say that again.
No, that previous.
New node dot previous
Equals last node.
equal to last node. Very good. So what Luba is saying here now is new node 12 here, previous is last node, right? New node 12, previous, right, is last node. Do we all agree?
Yes.
Yes.
Okay, are we done?
No.
What else are we missing?
Tail equals new node.
Tail equals new node, because we kind of jump here, right? Because this actually tail is here realistically, tail is here. So what Siring is saying, tail is no longer pointing to 8. Tail now should be pointing to 12. Let me just put a strong so we're not. Do we all agree?
Yes.
Right. Because tail is always pointing to the last node, correct?
Yeah.
And the last node now is 12, correct?
Correct.
All right. So now we say tail equal to new node. So how many steps we did here? We did 3 steps. We did 1. Yeah. 1, 2, 3. All right. 3 steps to achieve the continuation of adding more things to a doubly linked list that has more than just one value. Right. What's that?
Sorry, it's my nephew.
Any questions before we go ahead and write the code? Because basically we've gone through what we need to write, right? We started off with our function. We all participated. Somebody said we need to create a new node, some sort of new node to add to the thing. We did that. Matt and Christian said, hey, we need to guard against tail to make sure that tail exists. If tail doesn't exist, then guess what? Then tail just becomes new node, and head is also pointing to new node, right? So both pointing to the same node. That's the scenario where empty list, we add in one node. Next scenario, if we're not in, if tail does exist, what happens now? We need to say, okay, we have our last node dot next equal to the new node, right? And the new node previous, so now 12 previous is 8, okay? And then reassign what tail is, right? Because tail no longer is here. Tail no longer is here. Now tail is pointing to, now tail is pointing here. Any questions before we go code this out? The exercise we did here right now, this will get you through most of your DSA questions if you're able to draw them out and visualize where you headed, right? The interviewer will be very proud of that, just that, right? You showed where you headed and now you just have to code it out, right? Questions before we continue? Okay, let's go code this out. So we have our append. I'll do my best to just type exactly what we have here to see if we have any issues anywhere. So first thing we said, let's create a new node. And here we said let new node equal to DL node, which is value 8. Next, we said guard against that tail being nil or list being empty. That's the same thing, right? Tail being nil and list being empty is the same thing. So here we said guard, let last node equal to tail, else here we empty, right? Empty list. So our empty list, what did we say? We said head equal to new node, and we said tail equal to new node. Yes.
You passed an 8 instead of the value.
Oh, sorry. Why am I hard coding values in there? I see Syring somewhere. I blame Syring. Very good. Thank you. So here, value. This is good. This is good. Great. This is step 2. Just put a step 3 here. Append to empty list. So we're going on. Now we're not in an empty list anymore. If we at 51, at 51 we're no longer in an empty list. So here, no longer in an empty list. Oh, this list has values. So this is 4. In 4, what did we say? We said last node of next equal to new node. We said 5 new node dot previous equal to last node. And last step 6, we said tail equal to new node. And this is the whole function here. Any questions before we go ahead and test this?
These are all the like different cases. It's either empty or it has.
Yeah, either
nodes.
it's empty or it has nodes. Yep.
Okay.
Okay, awesome. Were we all able to type this out? Still typing?
No.
Okay. Let's write a simple helper function somewhere. Function at the very top here, just write function example. Here we're taking a string and we're taking some sort of closure. And here I'll just call my closure, I'll call in print, and I will call in print whatever string I passed in. This will help testing different methods. So just write that little helper method here, and then let's go test our append function. Actually, we don't have a print yet. We should have a print first. Did we type this out?
Yes.
No,
Okay.
not yet. Sorry. There's always one.
No problem. Gotta call this guy.
Alex, can you explain this function?
When you see it in use, it's gonna better explain itself. Basically, when we're testing out the append function, I'll just use this so that we have a print statement saying testing append. That's all this does. It's a function, it takes in a string. For example, the string I could pass in testing append, right? So that string just gets printed here. The action just calls this closure here, right? And whatever the closure has, it just executes it.
Okay.
Yeah. Okay, so going down, we have our append, but we don't have a print yet. So let's write a print function, because we don't have a print function yet. Let's just write print forward. Doesn't take in anything. It just prints out the contents of our Doubly linked list. We'll start off with a current node. Current node is head. Remember, as we're navigating through the linked list, we're navigating from head, correct? Everybody? I mean, if we're going forward right now, actually. Hello?
Yes. Yes.
Okay, cool. So we start from head if we're going forward. Let me just change my word in here. So we'll say while let node equal to current node. Here we change in, we increment in where we are. Node.next, and we'll simply just print out what the value is. What's the value? Node.value, terminator. Actually want this. Current node. And out here, we just put a print statement. How many nodes? Well, we haven't added anything. So how this print statement works is, for example, if my head is 5, it's pointing to 1, 1 is pointing to 10, 10 is pointing to 0. This is what the print statement is going to look like. Again, this is printing our Doubly linked list forward from head to tail. Okay. Line 68 says head, which is 5, current node. I use a while loop. I say current node, which is 5, 5, 5, go ahead and print yourself. Now 5 needs to go to 1. How do I make 5 go to 1? Well, current node gets assigned node.next. So now my current node is 1. I come in here, I print 1. In 1, I say, go ahead, go to 10. How do I do that? I say 1.next, which is 10, gets assigned to current node. I come up here, current node is 10. I go next, current node is now 0. This is 0. I'm done with my while statement. I print 0, and I'm done. Everybody with me so far?
Yeah.
Okay, cool. So this is print forward. And now, Luba, your question is going to get answered very quickly, very soon. Let's just test out a list. Let's just call it list. It's a Doubly linked list. On our Doubly linked list, the operation we could perform right now is, well, let me actually do my example. So Luba, the function we just wrote up here, example, we'll call it down here now, right? I'm going to call my function example. It takes a string. I'll put in a string. I'll pass in a string here. I'll call it testing append. It takes a closure. I'll use straight enclosure syntax. The closure doesn't take in any arguments, right? And I'm simply going to say list.append. What do I want to append? I'll use the same example we had earlier. I'll append 10. List.append. I'll append 7. list dot append, I'll append 5. And lastly, actually, that's fine. I'll just print it out now. List dot print forward. What we should get 10 pointing to 7, pointing to 5, pointing to 0. This is what we should get when we run this playground. If anything else, something went wrong, we gotta test it out. So if we were to run the playground now, run playgrounds, we got 10 pointing to 7, pointing to 5, pointing to 0. Did everybody get that?
Yes, sir.
No, mine failed.
Yours
Mine
failed.
too.
Did we run it? What's the error?
Expression failed to parse, unknown error.
Same. Same here.
Okay. Did we write the example here?
Sure
Yeah.
did.
For now, just comment this out. Let's see where we're getting this error. The only thing we should have now is like let list equal to W linked list, yes?
Yeah.
Mhm.
Okay, run your playground again.
It says the same error.
Where's the
Same
error
here.
coming from?
It says playground could not continue
think so.
because playground source did not compile successfully.
Is that, is there a line number or just like, no line number?
No.
I've never seen error like this.
Let's see.
Should we?
For purposes of anything, let me just slide this out. Is that okay?
Okay.
Let me just slide this out.
Yeah, I'm still getting the same error. Maybe I should I'm just gonna X this out.
Alex, I got like playground could not continue running because the playground source did not compile successfully.
Close
It's
playground
not-
and run it again.
I did.
Just put like a, comment everything out and just put like a simple print statement and see if that runs, if that compiles.
Okay.
I slacked out the where we are right now.
Yeah, I pasted Alex's code and it works.
Okay.
Same here.
All right. Let's just continue here because we did most of it. If anything else, there was something else happening there. Okay. So we were able to print out. Luba, was it printed? It printed out correctly, correct?
Yeah.
Okay. So now let's write a next function to really test out our doubly linked list. Let's see if we could print it out backwards. Everybody with me?
Mm-hmm.
All right, so let's write a new function called print reverse. Function print reverse. And for here, we're looking for 10, 1 to 5, 0. This is what we're looking for here. So reverse, okay. Current node, sorry. Head, same sort of logic, but a different pointer we'll be using. So current node, and here we'll say print node dot value, node dot value, node dot value, terminator, let node. How do we walk this time? What am I doing here? What am I typing in here on 80?
Wait, Alex,
Yes.
I have a question. The print forward should not be in the function and should not be in the class, right?
Yes, it should be.
It should be in the class.
Yeah, everything is in the class.
So can you go to the top of yours really quickly? And just from the append, just work, right?
Append, so append is a function in there. After that, we have print forward, and now we're writing print reverse.
All right, and the print forward.
Print forward.
Current node's head. Well,
Would it be current node equals node dot previous?
Yes. Although I was looking for somebody else, but that's okay. What's that?
I didn't participate in the last one.
The what?
I didn't participate in the last code.
Today, or just today. 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 Very good. Okay, so that's the difference here, right? Christian said instead of doing node dot next, because we're not going forward, now we're going backwards or reversed. We just say node dot previous, right? So if we started off at, well, we have a problem here.
We should start at the tail now.
We should start at the tail. Very good, May. Because if I'm starting head dot previous is what?
Nothing.
Nil, and we're done. All right, so we're starting at tail. So tail dot previous has, over here, tail dot previous has values. Very good. Awesome. So just always talk about your code. Even if you think you got it, go back through it and talk about it before you run anything. Right, talk out loud to that interviewer. All right, let us go test print reverse. So again, Luba, our little helper function we have, we could just say print reverse here. And here we could just say list.print reverse and run it. And now, so Luba, what it gives us a header, like a header for the example and whatever is in the closure here, same as print reverse. So now print reverse should be 510. Somebody forgot to put nil in here. So we need nil here, right? So after 10, just put one print statement here. If I run it again. If I run it again, 5 pointing to 7, pointing to 10, pointing to nil. So right away, we see a doubly linked list, right? The way to reverse is very easy, right? Because you have a pointer to reverse or a pointer to previous. So you just keep going from tail back to head, right? So there's definitely a lot of advantages of doubly linked list. That's why you'll see singly linked list more, because again, it's harder to do certain operations with only one pointer, right? But doubly linked list, there's 2 pointers. Okay, this is a good place to take a pause and give us some to-dos to do.
Wait, can you go back to?
Go back to, where am I going?
All right, you slacked this out, right? Sorry, never mind.
It's okay. Any questions before we kind of wrap this up? I'll give us some exercises to do on this particular class here. Any questions?
Sorry, no, but could you go back down real quick? I wanted to see how you, okay. All right.
All the exercises I'm giving us, please draw it out first, right? Draw it out first before we write code. Exactly what we did today. Go on your whiteboard, draw the thing out, and then test it out, then go ahead and implement the code. The code is the icing on the cake. The hard work is drawing it out on the whiteboard, right? Okay, so the to-dos, to-do number 1, to-do. We did append already. Let's do prepend. Prepend is what? What is that? Add a node to the front of the list. What does that mean? Well, what do we have? If we have this, right? Assuming this is our existing list. I want to add some value. I want to add 8. At the end, our list output I'm gonna say output. Well, new list should be this. Everybody clear?
Yep.
All right. Cool. Excellent. Let's do a next one. Two. I want to delete head. Well, what does that look like? If we have this, and I say delete head, at the end, it should be this. So this is existing list, and this is the new list.
Did you put these under append, or did you put these under all the functions?
Under our last function, print reverse. The to-dos, yeah?
Yeah.
Yeah. To-do 1, to-do 2, print, forward, we did that. Delete head. Well, this one is pretty straightforward. Tail. If I have this, and I say delete tail, then my new list yes? Hello?
Yes.
All right, cool. And I'll do 2 more. Do 4 and to do 5. What's the 4 look like? Well, to insert node, should I give us to do? Haha. Insert node after, insert value after some node. Insert value node. So if I have an existing like this, and I say insert what do I want to insert 3, and then node, some node, head, dot, next, something like that. Insert node, head dot next would be this, would be 10. So I want to insert it after 10. So at the end, it should be new list. This after 10. So this is head is 8. What do you pass in? You pass in head dot next, which is 10. So now 10 should be pointing to 3, like that. And I'm sorry?
I don't understand what's going to be passed. And
You're passing in a node. So in that case, the way you pass it, it needs a reference to what you want to pass. You'd pass in head dot next, or sorry, list dot head dot next. Over here, you have a list. We need access to this head. Please update your head variables, everybody, to get access to head. So now you have access to head here. Hello? Everybody do this?
Yep.
All right, so now our head is private, like I cannot change it, but I could access it. Remember set here?
Yeah.
All right, cool. So now if I have, for example, 4, number 3, number 2 is here.
Okay.
So if I have, number 2 is here. So if I have a function called, what did I say, insert some node, whatever. This, I put in some node here, which is a DL node, and some value, which is some value, right? To call this, I'll come right back up, okay, Tiffany, 1 second. So example here, insert after, say list dot insert. I pass in a node, list dot head dot next, and some value 3. This exists, so I put this to this, and this exists, so I put this to this. So head dot next, head dot next. Amini, does that answer your question? I'm sorry?
So if we wanted to, for it to be inserted after, you'd have to just keep adding like.
Yeah, or get a reference to it. It has to be the same reference, right?
Okay.
Yeah, as long as it's the same reference, because you, hint, this has to probably change, what is it? This might have to get changed to conform. You might have to conform to what? Equatable. Just a hint. But I mean, as long as you're a reference to what you pass in, because it has to be the same instance or the same instance that you're looking for.
Okay.
Cool.
What was number 4?
Number 4 is insert value after. That's what we're working on right now. Okay. And let's just keep it at that for now. That's enough. We also have capstone to do. So we have work to do for today and tomorrow with this problem, really. And if you are done, then you could do number 5 to do. Index, whatever index, right? Some index. What does that look like if I have this exists in this, and I say delete index 0, then what should be my answer? This should be gone.